I figured with this title, I can't hide for long that this is not a workflow talk. And I assume you would figure it out eventually. So I admit straight in the beginning. So it is about uncertainty quantification, Gaussian processes. There's some autonomous experimentation in there. But I hope that especially the uncertainty quantification maybe and the intelligent decision making it can be used for maybe helps as a tool in workflows. So this talk comes in several flavors, and that's why I have a little focus there, which is just kernel designs and scalability. Some of this might be more interesting for this crowd. Some might be less, but I try to make this talk relatively entertaining. All right, so I'm going to start with a little bit of a motivation. So we're going to talk about kind of stochastic modeling in general, but start with autonomous experimentation. I always start with that topic because when I was hired, now almost 6 years ago, into Lawrence Berkeley National Lab, that was the topic I was tasked with, and especially doing that for the DOE light sources. We're going to see Gaussian processes are going to come up. They already came up in the title, and I want to give some preliminaries on what they are. They're in some audiences they're really well known, and some others not at all. So we're just going to go through just enough stuff so that the rest kind of makes sense. Then we're going to talk about challenges. So it turns out over the last few years it has turned out, and that might be something that has turned out in all of machine learning, that just using certain tools doesn't always get you the best result. And that's no different for stochastic processes and Gaussian processes. So we're going to talk about some of the challenges when setting them up and when one wants to use them. And then really we get to the actual meat, and those are some advancements. So, and there we're going to talk about some kernel designs and how these kernel designs can help us with expressibility, reliability, and also scalability of the Gaussian process. And then right at the end, I want to talk about some synergy, community codes, and so on and so forth. So let's get started. And before we motivate anything, we really have to pin down just a little bit what we are motivating. And that's really that. That's what we're motivating. It's function approximation. It's uncertainty quantification via Gaussian processes. The general setting, and that setting is going to stay the same throughout the entire talk. So you can always keep this image in mind, is that we have some sort of input space. It's 1D here because it makes it easy to visualize. It's usually not. We have some data. Those are the blue little circles, and we are asking, what is the best approximation for our latent function? So the ground truth function here, we call them the latent function, and so we could ask, okay, what's here? And we don't only want some sort of one number as a guess. We want a distribution. So that's why it's uncertainty quantification. Of course, supervised machine learning. All techniques in supervised machine learning have this task, but we're especially interested in getting proper Bayesian uncertainty estimates for the function value at this point. And there are a bunch of functions it could be, but usually, yeah, so there's a distribution, and we want to evaluate the distribution for interpretation and decision making. And especially for decision making, of course, autonomous experimentation, now often called self-driving labs, or maybe self-driving labs are an extension. I don't think it's quite figured out yet. But autonomous experimentation is, of course, an application of such a stochastic view of a model function, because it's clear that if you have uncertainties over some sort of input domain parameter space or whatever, you can use that to make intelligent decisions. So generally, when I came in, again, almost 6 years ago now, I went to my first light source. That was the NSLS2, and this image is kind of what I saw. So you have an instrument. In this case, it's a synchrotron beamline. There are a bunch of little knobs you can turn on those, like beam shape and beam size. You have a sample, and the sample is made somehow. Synthesis parameters, environmental condition, and so on and so forth. And then in this case, it's a GSAX experiment. This is the one I saw back then, and you get these beautiful detector images out of it on the left-hand side. That's raw data, and usually that already back then, NSLS2 is a pretty cool facility. It was pretty new back then. It still is. And so there was some automated data analysis pipeline. But then a person would look at whatever comes out out of the analysis and would try to figure out kind of what's going on. Where do I go next? You could go somewhere where we haven't explored at all, or maybe you go somewhere where something interesting might be happening that what your intuition tells you. Okay. And back then, I think the example I saw was that there was a sample that went through an entire annealing history for 2 hours, and data taking was going on, and then you would end up with a property of a material, and now you would have to decide, okay, where do you go now? And that's of course a big space. You can change a lot about an annealing history, and that's very hard, of course, for the human brain to do, to know where I'm going in this gigantic space. There were some other things happening back then, usually, and that is still often the case for 2D examples. People scan through your parameter space, so you have a dx, dy, and then you just set it up at night, and it runs all night, and you explore your space. Sometimes, not very often, but if the space is 3 or 4 dimensional, sometimes people use random data collection. At least they make sure they kind of cover the space well. And then again, for higher dimensional spaces, annealing temperature is one of those examples. Intuition often comes in, and so my main goal when I was hired was, okay, we need something for them that will just kind of independent of this dimensionality, will help them make optimal decision, or even not only help them, but actually close the loop. They can go home, the experiment happens, and they can come back, see their model, and do the science. And so this is basically then the updated loop. It's not all that different. Everything has to be a little bit more robust. There is actually a good amount of workflow work going into this loop, but I in the end have focused my work and a lot on this intelligent decision making via these stochastic processes, and Gaussian process is an example of a stochastic process, and in combination with function optimization to kind of solve this problem. There's a software tool that came out, it's called GPKM, and I'll tell you a little bit more about that later. But let's have a look at some simple examples. They're all relatively, they're all now years old, and I would say they can now be called kind of like, almost like a standard. So at these places, I'll show you the examples from. This is now something users can use. So this is kind of what has happened over the last few years. This was Air Force Research Laboratory coming to NSLS2. Again, it was relatively early in the process. Simple 2D example. I'm going to show a lot of 2D examples because the visualizations are nice. There were bigger ones. There are 2 problems with the bigger parameter spaces. Firstly, often they just don't fit in a beamline. There's a hardware problem. How do you control data collection in a higher dimensional parameter space? And secondly, visualization. So a lot of the examples are 2D. So again, this Air Force Research Laboratory, that would have been a normal scan, 10,000 points. The Air Force tricked me a little bit, and so they told the NSLS2 collaborator that there's a region where they want to take more points, but they didn't tell me because I thought maybe I influenced the algorithm. But they wanted to see if the algorithm it takes more points in the regions that are kind of high grain size, and it worked out well here. And in the end, 1,500 points were collected. And we're going to see that as kind of like a pattern. You get to like 10 or 15% of the data you would normally collect compared to a scanning. The same then happened a little later at the molecular foundry for defect identification through autonomous scanning tunneling spectroscopy. Really same principle, very much, and also now available to users who will go to this particular microscope. Then there was an experiment that was at the ALS, angle resolved photoemission spectroscopy. Again, very similar setup. Again, it's very common with the beamlines. You have a kind of like a 2D input space, and you're asking like where should I go? And here you collect these gigantic spectra on the left-hand side. And they're so large you don't want to store too many of them. Again, normally you would scan over it. It's also expensive to analyze. So you're looking for something that does the data collection a little bit smarter. And that's what this autonomous experimentation is really all about. And I think this is the last example I want to show that is autonomous experimentation that's at the ALS, that is infrared spectroscopy. And yeah, again, it works very similar. You collect these spectra. You can do a PCA on those spectra and then try to find uncertainties in the PCA components across space, or you're looking for you're trying to go for like similarity measure of the interpolated spectrum, the learned spectrum, and the reference spectrum, and so you can find materials. And again, we see that the the advancement that's been made, the advantage of using it is similar here. We have about 5% data collection in about 10% of the time. And again, same story here. This is now available to users there. So autonomous experimentation is certainly a great motivation to look into this kind of UQ function approximation. But of course, there are other examples in the applied sciences that have not necessarily directly something to do with autonomous experimentation and self-driving labs, but they are really really great kind of applications of this idea. And I want to show two here I've recently worked with, and that is the one example we worked a lot on recently on batteries. And so it's especially when it comes to failure distribution estimation. And so we basically proposed that one could understand failures as or battery testing data as being created as one underlying latent function with a flexible noise model. And that latent function now, we're trying to find it based on the data that is being collected. The standard would just be, and I think that's the standard in industry, you just take one of those cells and you test it. But for warranty definition, to warranty a battery, you ideally want to have this failure distribution. And if you want that, usually what would be done is that you test is usually 24 batteries, and then you kind of fit a distribution just to their failures. You throw everything else away. You just fit it to the failure, to those 24 failures, and then you say, okay, that's my failure distribution. And here the idea was we can actually use all of the data that is being collected and see if we can find this underlying latent function, look at the uncertainties, and maybe there is a component of decision making here, because maybe I can say after a while, this distribution doesn't change anymore so much. So I have now understood the latent function that creates that data, and I can stop my test. So that was the idea here. And then also a project I'm working on these days is climate sciences and making stochastic models of the climate, which is challenging just because there's a lot of data. There's a lot of physical knowledge involvement, so we can't just use any learning algorithm. It has to be domain aware. It has to be able to deal with a lot of data. Ideally, it can extrapolate, but not put too much bias on the extrapolation, because often the question is, how does the climate change at a certain place into the future? And so it has been very beneficial for me and I think for my collaborators to work on these stochastic models in the climate sciences. All right, so I hope I was successful motivating that we are looking at stochastic function approximation and looking at uncertainty quantification. And so one of the most popular way of doing this is the Gaussian process. And we'll see why. And so I want to explain a little bit what the Gaussian process is all about. The Gaussian process is, again, the most popular member of the family of stochastic processes. And stochastic processes are all based on the idea that I put a prior probability distribution over a function space. And because that always sounds a little abstract, we usually think of it as placing a joint prior probability distribution over function values. And so that means if I, for instance, measure 100 points of a function I'm interested in 50 more, I could think of it as placing a prior over a 150-dimensional space. So that's kind of the idea behind it. And for a Gaussian process, that is a normal distribution. And these functions I'm considering, in that case, those are all superpositions of kernel functions. So we have the alpha here is alpha I k, and those k's are so-called kernel functions. And I'm going to talk a lot about kernels because they're kind of the core concept of how you can customize the Gaussian process really to do what you want it to do. So these functions are superposition of kernel functions. Those kernel functions, and there's a big misconception about them out there, they don't have to look Gaussian themselves, like a Gaussian bell curve. I hear a lot that people think the Gaussian process is called that way because the kernels look like a Gaussian bell curve. But that's not the case, and that's why I drew them here in kind of a different shape. So really to make clear, this is not the case. They don't have to. It's actually a very flexible function class themselves. And we think of them again as kind of basis functions, and then the basis functions are centered at data point locations. But the cool thing about them is because of their characteristics, they are also covariance operators. So whenever I have 2 points and I have 2 basis functions centered there, the outcome of the kernel is also a covariance matrix entry. And what do we need more than a covariance to define a normal distribution? Nothing, maybe the prior mean, but the prior mean is often assumed to be actually a 0 or a simple constant. So the kernel for us delivers the covariance, and we're going to talk about this more as well. And so it plays this dual role of being a basis function, being what allows us to approximate a function, but also at the same time giving us these uncertainties. The kernel also depends on this h here. These are hyperparameters. These are basically the free parameters in a Gaussian process, so I don't actually have to find these alphas, but I have to find the set h, the hyperparameters. And these really change the shape of the kernel and therefore the shape of the entire normal distribution. So it's very, very important, and I train this usually by maximizing some marginal log likelihood. There are other ways of training, but that's the standard method most people go with. And so that is really, so training really means changing the shape in the end of this prior until the likelihood of our data is maximized. And then when I condition that very prior, I get this approximation. Some people call it a surrogate model. It's the posterior mean, so it's kind of our best guess of the model given the data. And then, of course, the posterior variance, which is the uncertainty everybody wants to get out of. Let's talk a little bit about the kernels. Why are these kernels so important? A Gaussian process wouldn't really exist without the kernel method framework, right? And the reason for that is that we have to place a prior not only over the data, but as I said earlier, if you have 100 points and you are interested in 50 more points, you've never measured them, you've got to place the prior over all those, over 150-dimensional space. How do you do that? And that is by using what is called the kernel trick. So the usual definition of a covariance matrix is up here, and we see that explicitly the random variables show up in the definition. Now, well, that's not great. We've never measured those function values, so we don't have them as a random variable. We don't have them at all. So what we do, and again, that's called the kernel trick, we are training, by finding these hyperparameters, we're training a kernel function to approximate those covariances. And these are functions only of 2 input points. So if I now know where I am interested in a function value, that is enough to now extend this prior covariance over those dimensions. Perfect. And so these are positive semi-definite functions, and we're going to talk about this more. This is really important, otherwise they couldn't be covariance operators. And in about 95% of all applied studies, that's also very important for the rest of the talk, these are chosen to be stationary, and most often the squared exponential kernel is used. That's just what everybody's using. Probably has something to do with that if you install scikit-learn and you go through the examples, that's the kernel they're using. So lots and lots of studies have been done with this squared exponential kernel, which is a stationary kernel. And part of the talk is going to be about how to get away from this, how to not use stationary kernels. Either way, so we have seen we always have the surrogate model available. From the first data point on, we have a surrogate model that's posterior mean, and we have uncertainties. And back to the framework of an autonomous experimentation, of course that is very valuable. You can now define an acquisition functional that's a function of the entire posterior. And you can combine this with what you want to get out of an experiment. So you could look for a particular material characteristic, for instance. Minimize, maximize a certain one. You can look for curvatures, high gradients, whatever you want to do. You define these acquisition functionals, plug them into an optimizer, usually constrained to kind of mostly to protect the instrument and to not get into too high cost regions of the parameter space. But basically, it develops, it gives back to you basically the maxima. And those are then communicated to the instrument, and you're basically closing the loop. So this is a very typical application of the Gaussian process. All right. Cool. So we have motivated stochastic function approximation via Gaussian processes, and we have now learned what they are. Very good. They do come, as we will see now, with a whole lot of challenges. Number one, accurate uncertainty quantification is not achieved with standard GPs. And that would be a pretty controversial statement if this was a GP crowd. Normally, they are assumed to just deliver pretty good uncertainty estimates. So we see on the left-hand side, we see a ground truth, and that's the topography of the United States. And then we see the uncertainty at the bottom. And what we would want to see as humans, I believe, is that the uncertainty kind of reflects the underlying characteristic of the latent function of the topography here, but we don't at all. All we see is that the uncertainty is high in between data points, when data points are far away from each other, which is not wrong, but it's certainly not all we would want to see. And on the right-hand side, in the top, we see, on the right-hand side in general, we see the same principle, just in 1D, and we see in the top, so there are kind of three parts of this function. Kind of high curvature, high gradients on the left and on the right. I'm just going to call this wiggliness. And then in the center, we have kind of like a smooth part of the function. And ideally, we would, again, want to see that somehow reflected in the uncertainty. But the top, certainly, that doesn't happen. The uncertainty is relatively high in all of those regions. It's kind of averaged over the entire space. And on the bottom, we see that's much more like what we would want to see. The uncertainty is much lower in the smooth region. There seems to be a knowledge of what that function looks like. And we're going to talk about how this is achieved later. Number two, standard GPs don't adhere to physical constraints, so that's a little unfair. How would the GP know about certain physical constraints? And here the example is symmetry. So this is Ackley's function. That's a typical test function in optimization. And it is, of course, symmetric. And a standard Gaussian process we see on the right-hand side, this is lost. And of course, ideally, if we have knowledge like this is a really strong domain knowledge. This is great knowledge. We would want the GP to be aware of this kind of symmetry behavior, of course.
Marcus, just a quick question.
Oh.
By standard GP, you mean exactly
very good.
RBF?
Very good question. Yeah, pretty much stationary kernel and constant prior mean. Thank you, though. I did forget to define that. Number three, standard GPs might not have optimal solutions or solutions at all that satisfy optimization constraints. So here it gets just a little complicated because now we have a second kind of physical knowledge. The one was a constraint on the function space itself. So underlying a Gaussian process is the so-called reproducing kernel Hilbert space. It's that function space that is full of all the superpositions of the kernels. And the first constraint was about allowing only certain functions to even be in that space. No other function will even be considered. Now we're talking about different constraints. Those are optimization constraints. Those are the same constraints some people use in neural networks when they train the neural network and they say, but it has to satisfy a PDE, an optimization constraint. And we see that the standard Gaussian process will either sometimes doesn't have a solution or has a solution only far outside a constraint. So here, what I'm doing, I have a latent function and it's monotonically rising, so it's never dropping. And the standard GP doesn't know that. It's the blue curve. And when I now plot, I'm going through, I can now plot the landscape of hyperparameters and of the marginal log likelihood of the marginal log likelihood. That's what I'm optimizing to train the GP. And this is on the right-hand side. And the standard kernels, they have a length scale and they have a signal variance. And I find the solution just fine with my optimizer. And then I'm going through this space, right? Instead of optimizing, I can go through this space on a grid and can ask every time, which functions would have satisfied the constraint. And it turns out it's over here in this region. So the actual solution is quite far outside of this function that would actually satisfy my physical knowledge. And again, this is an example I had to look for a while to find one where there is a region that actually satisfies the physical knowledge, but the optimal point is far away. There are lots of examples, and we're going to see one later, where there is just none. You try to optimize, you have this constraint optimization, and it just tells you, the optimizer just tells you it can't find one. There is no candidate solution that even satisfied the constraint. A big problem of standard GPs. Number 4, GPs don't scale well. Everybody who has ever tried to set up a GP of 10,000 data point, maybe 20,000 on a laptop, laptop crashes. That's not great. So here we have there are big data sets, especially in the climate sciences. One we recently worked with 5,000 climate stations, 10,000 days. And it would have taken 625,000 desktop computers, average desktop computers, to just store the covariance matrix. Like it's too large. And that's just the storage. That doesn't even include the downstream computations. We have to solve the log dead, and we have to solve a linear system. So that doesn't even include that. But even just storing it is hauntingly expensive. And then if we're actually going this step and we're saying, okay, we want to improve certain things about GPs. Maybe we are thinking about a kernel. Maybe we are thinking about a better priming function. Then what happens is, of course, we have to find more hyperparameters. And now it turns out that the landscape of the log likelihood, which is, by the way, on the bottom left here, it becomes really complicated. And so it is very common to train a GP with very simple optimizers, local optimizers, which here would have worked just fine. In A, we see where still kind of the standard kernel is used, signal variance, length scale, and we find a solution, great. If we now use a kernel I'm going to introduce later, it has way more hyperparameters, and now we are pretty much slicing through that parameter space at where I found a solution. Here, it's not the parameters, it's the parameter, it's the space of the hyperparameters, right? It's the landscape of the log likelihood you're training. We see there are lots of solutions, some of them in saddle points, some of them look, at least in this view, they look like real optima, but we don't know, we don't see the other dimensions. And that is in C, and in D we have a different view, and we see many more local optima. So these are very non-unique optimizations. And so kind of standard optimizer, just purely local, often, and certainly genetic type kind of optimizers won't really cut it here. And even after all my best effort finding this solution, I looked at the eigenvalues of the Hessian, and I saw that they changed signs. So I only found a saddle point in this case. Okay, so we have these kind of summarizing the challenges. We have these 5 very interesting challenges. We have the inaccurate uncertainty, the physical constraints, the optimization constraints, then the GPs don't scale well, and we have the tough optimization problems. And those are in a green frame here because I'm going to try to address those in the last 25 minutes I have. There are 2 really interesting other challenges about GPs, and they came up so recently, and we've been working a little bit on them, but they're not ready kind of to put them in a talk. So, but I'm happy if somebody's interested in that stuff to talk about it later in the break. So there's 6 standard GPs don't work on nonlinear spaces. That's really interesting. So the moment we have, we want to do a GP on a, nonlinear space, a rotational ellipsoid, there are some solutions for a sphere, but anything that's kind of like a compact Riemannian manifold, more flexible, just kind of curved, and not necessarily a parametric kind of way, then the entire GP framework breaks down because the kernel aren't positive semi-definite anymore, and so I can't use them. And there's lots of research going on trying to find positive semi-definite kernels on these spaces, but there are some approximation methods, but they've turned out not to be practical. So this is a huge problem here. And then, of course, you've probably been wondering, a normal distribution is a pretty big approximation for some data sets. And of course, there are situations where Gaussianity just doesn't cut it. And I'm here not talking about other kind of closed form distributions, like Poisson, for instance, but I'm actually talking here about much more flexible ways how to define priors. And that is also something people have been working on, and our group included. Okay, but let's tend to the 5 big challenges in the top and see if we can find solutions to any or hopefully all of them. Okay, and our main tool we're going to use to solve these challenges is the kernel. And I hope now it makes sense that I gave more information on kernels earlier, and I'm hoping I really did do that. Okay, so there are basically two different kinds of kernels. We heard about stationary kernels here in the top. Kernel number 1 is a pretty typical one, the squared exponential kernel. And all you have to really know about stationary kernels is that they only depend on the distance between 2 points. So in the topography examples, the expected covariance between 2 function values in the US, in the Rocky Mountains, would be the same if they are 5 miles away as they are if they are in the Great Plains. That already sounds a little suspicious. That just doesn't sound quite right. But that is the standard kernel. And I should also mention, I should have mentioned that earlier, Gaussian processes are the foundation for Bayesian optimization. So all the things we are talking about here affect Bayesian optimization directly. Anyway, so we have kernel number 1 is a typical stationary kernel. Again, we just spoke, it only depends on the distance between 2 points, not where they actually are in your input domain. And then we have kernel number 2. This is one of a very popular. So the spatial statistics community, they are very active developing a certain kind of non-stationary kernel. And kernel number 2 comes right from there. It's a very powerful kernel where the length scale, the level of anisotropy, and the signal variance, they can all change over all a function over the input space. Kernel number 3 is often cited to be the motivation for deep kernel learning. In that case, G here is a neural network. So a neural network that basically takes your original input points and can nonlinear transform them, and that transformation goes directly into the kernel. And then that kernel is often stationary, but since the axes are transformed, the original kernel is now non-stationary. And kernel number 4 is one of my favorites. It's just a product of a function applied to x1 and applied to x2. And you actually see that kernel number 4 is in kernel number 2 here as the signal variance. So that's a really cool kernel that you can just combine in so many different ways with other kernels. And this is actually a general statement because kernels, you can do a lot of things with kernels, multiply them together, add them and stuff, and kernels stay kernels. So you can do a lot with these, combine them, and kind of see what happens. And these functions f and g's, they can also be any sort of function over your input domain, which is a great strength. So they can be neural networks, radial basis function, piecewise constant or linear, which gives those non-stationary kernels great flexibility, but also makes them computationally pretty expensive because one of the strengths of stationary kernels is that you will only always have very few hyperparameters to train. It doesn't matter what the dimensionality of your input domain is, which that flies out the window. Suddenly you have functions over the input domain, so you have way more hyperparameters you have to deal with. Okay, and now I might be a little biased because that's obviously the stuff I'm working on, but customized stationary and non-stationary kernels, I feel, can really give GPs superpowers, and we're gonna see why that is. Okay, let's look at some of the. Let's go back to the problem of reliable uncertainty quantification. Here we see again the example from earlier. It's a 1D example, and we see a stationary kernel working all the way on the left-hand side, typical Matern style kernel, and we see that that's what we don't want to see. It seems like the uncertainty here in this relatively smooth region seems too high. It is smooth. Why do I need so many points to pin down what the function is there? Here we see something much better, and that's the example we saw earlier. And this is actually very simple to do this because this is the kernel. It's actually this k-stat is the same as over here, and the function is just the sum of 3 radial basis functions that are located here, here, and here. And that's all you have to do. It's actually not that many more hyperparameters. You get a way better function approximation. And then on the right-hand side, we have a deep kernel. So that means that's the kernel. It is the distance only, but again, G is a neural network here, so the input domain has been transformed. And this is a very, very simple one. I played around for a while, and we see it picks up very well on the wiggliness on the right-hand side of the domain. Not so well that it starts here on the left-hand side again, but it still does a pretty good job in the function approximation department. Yes, again, so one of the big challenges with deep kernels, if you ever get to set one up, Gaussian processes are, one of the reasons why they are so popular is that they are very interpretable. In the machine learning world, relatively interpretable. You get these hyperparameters, you kind of know what they mean, great. And that stays the way for all stationary kernels and for parametric non-stationary kernels where this function is a parametric function, it's a sum of radii basis functions. The moment you, of course, bring a neural network into the mix, you get great flexibility from the neural network. The negative thing is suddenly you have this problem of that it is not interpretable anymore because you suddenly have a neural network, and it's kind of hard to wrap your head around what it exactly does. But overall, I wanted to mention the deep kernel here is because I believe they have a great future and will play a great role moving forward in the kind of the Gaussian process world. So let's look at that same principle we just discovered in 1D. Again, back to our US topography example, and so we see again the US topography on the top left side. We see the kernel. That's the same kernel we just used in 1D. Just we have to adjust it slightly. Again, now non-stationary kernels do depend on function over the input space, so now it's 2D. So that is slightly that just changes those numbers and where those basis functions are located. Otherwise, it's the same kernel. Here in the left column, we have the performance of the stationary kernel, non-stationary kernel right here. We see it's a little sharper over here. We see the error is about half. That's great. But the kind of key takeaway of this, and that is, I think, the first key takeaway of this talk, is the uncertainty quantification. And so let's blow it up a little bit so we see better what happens. This is exactly from earlier what we don't want to see. We don't see any characteristic of the underlying function. A very change in the kernel definition, a very simple change in the kernel definition, leaves us with this. The uncertainty, this is the same color scheme and scale. So first we have lower estimated uncertainties, and we have all the high uncertainties in kind of the Rocky Mountain area. And that is probably where high uncertainties are, because it's all really, well, mountainy. And on the right-hand side, we have almost zero uncertainties because it's relatively flat, and data just counts more. We have about the same data density across the domain, so it should be smaller uncertainties. Not like here, where this uncertainty and this uncertainty is pretty much the same magnitude. That's not okay.
So the measured points, I would assume, corresponds to those small black dots.
Right, everywhere. There are many, but they are like kind of clustered all in the blue regions, right? And so you can now imagine if we quickly go back to a self-driving lab, autonomous experiment, and now we go and say our acquisition function says, well, go where uncertainties are high, right? We would go through all of these. A very costly process. And we think we did something really smart because we're using a smart algorithm to make decisions, but a slight change in kernel design would have actually been much better. Uncertainties are lower, and we actually would almost only focus on this left region. This is a great uncertainty already. So this is a great kind of takeaway that non-stationary kernels are really, really worth it if they can be applied. Okay, so number one is applied. Let's talk about the physical constraints. A typical example of physical constraints, and we talked about that earlier in the example, is symmetry. And it turns out kernels can also take care of that problem for us. So this is an example from ILL. This is a neutron scattering source in Grenoble, France. And we have, in this case, they did do a ground truth scanning. So that's why we have the ground truth here in the middle. That's real data. It's approximately 6-fold symmetric. And they often have symmetries in neutron scattering. And so in the beginning, they used kind of the standard Gaussian process. And look at this. This is 200 randomly chosen points, by the way. And yeah, it looks absolutely terrible. It doesn't resemble the ground truth at all. So now all we change, we have the same points. It's exactly the same data. What we are using a kernel that makes all functions in the reproducing kernel Hilbert space, that's the underlying function space of the Gaussian process, be 6-fold symmetric. So it doesn't even consider other functions as a posterior mean. And look at that. No added computational cost. Suddenly, we see here, this is 6-fold symmetric. That's awesome. And it becomes more obvious, this whole thing, when I only have data in the top right of the domain. Again, same ground truth. Looks terrible, the approximation using a standard Gaussian process, stationary kernel. Stationary kernel not constraining the reproducing kernel Hilbert space in any special way. This is also a stationary kernel, but again, it is constrained so that only functions that are 6-fold symmetric are considered, and we see beautiful 6-fold symmetry, and data is kind of magically, or information, not data, but information is magically kind of propagated into these areas. So this is exactly what we want to see. And this was used at a recent, well, it cannot be loaded. OK, we have the right, though. This was the right-hand side of the slide. This was used at a recent example at NSLS2. So that was NIST came to visit at NSLS2. And we did an autonomous experiment. And there were several things known so it was a 2D domain. We have in 1D, we have a periodicity, but the period isn't known beforehand. And the periodicity, the period changes in the x direction, and it changes linearly, but we don't know by how much. So the task was to find a kernel that is that constrains the function space to periodic functions, and at the same time, though, find that period and let it change linearly and find by how much. And this has worked really, really well. We see it here that this is using that particular kernel, and we can compare it to other methods, and we see that very early on the structure of the sample was figured out. NIST told us later that one could have stopped this experiment super early because they saw what they wanted to see. We went further to see when do these three converge, and so we went to 3,300 points. But a great example of how just using a different kernel, not many more hyperparameters, the training didn't take much longer, almost really nothing negative really happened, and the benefit can be really great just by thinking a little bit about the kernel that is being used. OK, so these physical constraints by reproducing the kernel Hilbert space are covered. It can be done by really powerful, these are stationary kernels, or sometimes we just saw an example of a mixture which makes it non-stationary. And let's talk about the standard GPs that might not have optimal solutions. And I want to do that by showing an example. And we had an experiment, and that was this CFN and NSLS2 again. That was a really interesting example. The original input space was 5D. We did it kind of in a two-stage autonomy where we did autonomous exploration in 2D and then in 3D, kind of in stages. And so, but what was explored was a 5-dimensional space. It was a SAX experiment, and every time when such a SAX image comes out of here, it looks like this. It would be radially integrated, and then you have a 1-dimensional signals. Those would be clustered, and then you came up after a while with 8 clusters, and now the Gaussian process was tasked to understand or approximate the 8 distances to those clusters for a new signals you haven't measured yet. So that was the goal. And because we split it up, the autonomy in 3 plus 2D, the rest here is considering 3D subspace. And in that 3D subspace, there were several physical constraints the scientists came up with. And that was partly isotropic, partly anisotropic. The new model function has to be is constrained between 0 and 1. Summing across the task, 8 tasks, the sum has to be 1. That was kind of a tough one. And there was a first order of differentiability in all directions of the model function. And so we set up a standard kernel and optimized and checked the model and always checked is the constraint fulfilled, and it never was. There was no such function. So we started playing around with non-stationary kernels, making them more and more flexible, and that's in the end the kernel we came up with. And that F here is a sum of 280 radial basis functions, similar to the topography examples, but here in 3D. And it turned out then we finally found optimal solutions that actually did satisfy the constraint. And here we just have 2 snapshots, since the sum has to be sum over 8 tasks had to be 1, and in this case 6 tasks were pretty much 0, so the remaining 2 pretty much had to alternate, and we see that worked just fine. So this was a typical example where you really had to add a lot of flexibility to the kernel to even find a function approximation that would satisfy a physical constraint. Okay, number 3, I see I have to speed up a little bit. Scaling. Now we talk about GPs don't scale well. And so there are a bunch of solutions to that, and they're all approximate solutions. So you might have heard of Vecchia approximations, inducing point methods. They're all approximate methods to scale GPs up. And so we thought 1.5 years ago, I wonder if by just working with the kernel definition, we can make exact GPs scale up to millions of data points. And so we set out to do this, and we were like, OK, now we have some experience already in flexible kernel design and non-stationary kernel design. So can we not add compact support? So can a kernel not be 0 outside a certain radius? Because that would then mean, if I make it flexible enough, that the algorithm can learn through training that things are not just correlated, but things are actually uncorrelated. They have 0 correlation. And if you make this flexible enough, maybe you can discover, instead of induce, a sparsity in a Gaussian process, which you can then use in downstream computations. So we did exactly this. We found this kernel. I'm skipping the equations here. If somebody's interested, I'm happy to share them later. But we can see they are compactly supported, so they're 0 in certain places. And when we think of a standard kernel, the stationary kernels, they have support everywhere, so they're nowhere 0. So it is not even possible. It's not the fault of a Gaussian process, I always say, that a dense covariance matrix come out. We just don't give it enough flexibility and compact support of the actual kernel functions. So we combined this kernel with distributed computing, in which you split up your data sets in parts, you ship them to different nodes. The covariance matrix batches are computed there in a dense format because it's faster. They are small enough. Then they are cast in a sparse format. They are sent back to kind of a host node, and there it's assembled into the big covariance matrix. And now this one is very sparse, and you can do your the linear system solve and the log-det. And you can combine this and this is just to protect your system, you can combine it with bias or constrained optimization to just protect your system. If it turns out there is no sparsity or not enough sparsity in your system, you don't want to crash it. So you can make sure with some constraints that you stay in a region where you do have sparsity in the matrix. But again, that is then basically you automatically transition into an approximate GP, and it's not exact anymore. But if it doesn't hit the constraint, it stays exact. Okay, so GPs don't scale well. We have done, and now we can attend to the optimization problems. We have now seen flexible non-stationary kernels giving rise to hundreds of hyperparameters, sometimes thousands. The optimization problem is really hard. It's ill-posed. There are a bunch of optima. Some of them are plateaus. Some of them are ridges. And evaluating the marginal likelihood is very costly. So we set out again to create an optimizer that would deal with these challenges. This work originated long before I worked on Gaussian processes, but it just happened to fit really well, and we kind of recast it here so that it would work for Gaussian process training. And how it works is it's a distributed algorithm. You have a bunch of walkers, and you send them to different workers on your supercomputer. They all do local optimizations, gradient-based or Newton, quasi-Newton, whatever you'd like. They find optima. They deflate them. And optima, by the way, it's also saddle points. I heard earlier yesterday talking about searching saddle points. So this algorithm works for saddle point search. You find the optima, and then the key is you can deflate them. It works by applying a deflation operator. The deflation operator is based on a bump function. You can effectively remove the optima after you found them. And then a global optimizer can come in, replace the fittest individuals, and they're the local, again, fully parallel, start again in a distributed way, finding new ones. And what you end up with is this ever-growing list of optima, which is sorted. You always have the best optima at the top, but you get really a good idea of the kind of distribution of optimal solutions. And also, if you allow it to calculate the Hessian, at least at the top, at least at the optimum, it will classify those optima for you. So that's a saddle point, that's a minimum, that's a maximum, whatever you need it to be. We also implemented this algorithm in such a way that it's non-blocking. So if you run this algorithm and you say optimize, the cell in Jupyter instantly will release, and you can do whatever else in this same code, and you can always just query solutions as you go. So it's a non-blocking execution, which is really helpful for autonomous experimentation because you don't want to go into a training and it takes forever and your instrument idles. So that's not great. Oh, I have 1 minute left. Great, we did actually manage to address those first 5 challenges. We've not spoken about 6 and 7. Wouldn't be possible anyway. I wouldn't be ready, but maybe in a year I can come back and talk about these last 2. 30 seconds about synergy. This is work with a ton of collaborators. I had to start at some point writing down names because it went way over 100. This has been like across institutions. Lots of people using it. So the autonomous experimentation community is really helpful, but also other communities using Gaussian processes and always communicating to me what's needed next and how it could be achieved. So tons of institutions here, so much so that at some point we started having a community for autonomous scientific experimentation called CASE. If you're interested in any of that, we have regular seminars and like, we can talk, you can reach out, lots of people post, job posts and stuff like that. If you're interested in any of that, go to autonomousdiscovery@lvo.gov. And last but not least, there is a software for all of this. This is how I do all my testing. There's 3 softwares actually. HDDL is the optimizer. FVGP is this Gaussian process engine. FVGP stands for function valued. So it's basically a multitask or extension of a multitask Gaussian process engine. And then we have GPCam, which basically wraps those two to create an autonomous experimentation framework. And GPCam, though, will install all of them for you. GPCam.lvo.gov is the website, and you have a little bit of a minimal code. This is kind of the minimal code you would have to write to start an autonomous experiment. So it's a fairly simple algorithm, but with almost unlimited customization options. All of the ones I spoke about for sure in this talk. Okay, key takeaways. If you ever find yourself setting up a GP, try to use the non-stationary kernels. Think about domain awareness. That's super, super helpful, especially in data sparse scenarios. But be aware that especially these optimization constraints, they do need extra flexibility. So you basically go back to your non-stationary kernels and make sure they have enough of that flexibility. For large problems, there is this naturally occurring sparsity often. Think about how to use that for your benefit. And then really, as these GPs grow in complexity, really think twice about which optimizer you should use. Normally, purely simple global ones and the local ones, they often don't cut it anymore. Of course, I thank the funders for the money, and that was it. Thank you very much.